infinity, our objectives today are going to be to use limit notation to describe end behavior of functions and identify horizontal asymptotes for polynomial, algebraic, rational, trig, exponential, and log functions. We're also going to use analytical methods to calculate limits at infinity. Limits at infinity occur when the independent variable becomes very large in magnitude. They determine the end behavior. So let's look at the first example. When we look at the function f of x equals 1 over x, we've got two separate stems to this graph. And in limit notation, the limit of the function as x approaches negative infinity as our function, as x approaches negative infinity, our function approaches 0. And the same notation is consistent on the other side, and I believe we have the same limit. As x approaches positive infinity, that function also approaches 0. That's an example of end behavior, and in this case, that forms a horizontal asymptote. So you should be able to use limit notation to also describe the end behavior of each of the following functions. Polynomials with an even degree and an odd degree. So degree is the highest power in any given polynomial. So here we have 4, here we have 3. If you have an even degree with a positive leading coefficient, positive 3, our end behavior would look like that. It would be headed upward on both ends. So the limit as x approaches negative infinity of p of x would equal infinity. The limit as x approaches infinity for p of x would also be infinity. So we've got, this right end behavior and the left end behavior. Okay, with q of x, we have a negative leading coefficient with an odd degree. So the end behavior on this, if you have a positive leading coefficient with an odd degree, that's what we'd get for end behavior. But we have a negative leading coefficient, so what that means is our end behavior will be up to the left and down to the right. So our limit as x goes to negative infinity of q of x would be positive infinity, and the limit as x approaches infinity of q of x would be negative infinity. Now the limit is determined by the behavior of the leading term, and why is that? Because as x approaches infinity, the leading term, which contains the degree of the polynomial, becomes more powerful. It overwhelms the other terms. So if I take x to infinity, what you could really think of this as is the limit as x approaches infinity of the highest power on the top over the highest power on the bottom. And you could then do some reducing. If you had the same power on the top and the bottom, it would reduce to the ratio of their coefficients. So as x goes to infinity, it looks like there would be a horizontal asymptote here at 3. In this next example, again, you can do some work with reducing a little bit. Highest power on the top. Let me first write out my limit. Limit as x goes to infinity. Highest power on the top, highest power on the bottom. This would be the same as the limit as x goes to infinity of 1 over x, which of course, as x goes to infinity, would go to 0. Now, something interesting happens here. The highest power on the top is larger than the highest power on the bottom. You might remember from pre-calc. If you have a power on the top that's larger than the power on the bottom, you're going to get a problem. You're not going to have you're not going to have an asymptote in this case. You're going to end up with, if I reduce this, it would be negative x squared over 2. If I plug an infinity in there, that clearly will go to negative infinity and thus will not exist. Let's take a more analytical approach to this and use what we call dividing by terms x to the n power, where n is the largest power in the denominator. Okay, limits at infinity for rational functions will help determine horizontal asymptotes. So let's go ahead and do that here. I'm going to take the highest power on the top and bottom. I've got x squared on top, and I'm actually going to just negate that 1 there and take x plus square root of x squared, which will come out to be x squared over, looks like 2x. That clearly, when we reduce that, would be taking a limit of a higher power on top, so that would be x over 2 when I reduce one of the x's, which will come out to be infinity and does not exist. Right? So if I input an infinity right here, infinity over 2 would be infinity and wouldn't exist. Example 5, I'm just going to look at the graph of this. When I take the limit as x goes to infinity of e to the negative x, I've got a graph that looks like this. Clearly that's going to go to 0. Another way you could look at this is the limit as x goes to infinity of 1 over e to the x. Right? So if e to the negative x has a negative exponent, we're going to bring it down to the bottom and change the sign of that. 1 over e to the infinity would be 0. Natural log of x, we're going to again look at the graph here. Natural log does this. And it's tempting to think that there is a horizontal asymptote, but there isn't. So this will be infinity, and therefore does not exist. And here's an interesting example. What I would do in this example to evaluate this limit is I would use properties of limits and split it up. And write it just like this. And there's a little quirk here that you're gonna want to be careful for. Okay, so this limit right here, if I were to plug in infinity, that would go to 5, right? Because the x's would cancel, and so we'd get 5. The limit over here, if I were to do direct substitution, if I plug infinity into sine over infinity, think about what sine x is doing. It's oscillating, right? The highest value could be is 1, the lowest value could be is negative 1. So if I have a value, let's say worst case scenario of positive 1 over infinity, or the other end of the spectrum, negative 1 over infinity, what that's going to do is just basically go to 0. So the limit of this would be 5, or the denominator. Okay, so I want to talk a little bit about horizontal asymptotes. A horizontal asymptote happens when we have an infinite limit, or a limit at infinity. If it equals if our limit at infinity equals some finite value. So let's take this function that's given, and if y equals b is a horizontal asymptote, the graph of f, find b. Well, what I'm going to do is I'm going to just do a portion of the foiling here. So I think you would agree that if I foiled the numerator, I'd get a negative 2x squared plus a bunch of stuff. And then in the denominator, I'd get x squared plus some stuff. And really, I don't need to FOIL out the rest because these would be the leading terms. So if I were to simplify that, it looks like that limit would be negative 2. And I'd cancel out those x squareds and I get negative 2. So it looks like b equals negative 2. let f be the function given by this, where a is a positive constant, such that the limit as x goes to infinity is 2/9. Okay, so again, I'm going to take the limit as x goes to infinity, and I'm going to do just a short FOIL here. This would be 2x squared plus some stuff. All I care about is that leading term. On the bottom, I get negative a squared x squared. At the beginnings of FOILing the denominator, what would I get? I'd get the limit as x goes to infinity of 2x squared over ax squared. Well, the x squareds will cancel. Looks like I'll get 2 over a. I know I want my limit to be 2/9. Oops, it should be 2a squared over, or 2x squared over a squared x squared. So it looks like I want a squared to equal 9, so a would equal 3. Okay, for example 10, for which of the following does the limit of f of x as x goes to infinity equals 0? Okay, we just need to know some stuff with what overpowers what. So exponential functions are always the most powerful. So e to the x is an exponential function. Which is more powerful, x to the 4th or x to the 5th? Well, x to the 5th, right? But when you're not talking about polynomials, so this would converge, the limit of this would converge to 0. So I'm looking for most powerful in the denominator. Alright, so let me erase this. The natural log of x is not going to be as powerful as x to the 100th, so the more powerful function is in the denominator, so the first one is yes. E to the power of x is much stronger and will overtake natural log of x, so this would be a no. And e to the power of x will overpower x to the 100th, so that would be a yes. Alright, let's look at this last example, finding all horizontal asymptotes. So I would probably look on the left side and the right side to see what's happening, what the behavior is. So let's look at the left side first. And see what's happening. So if I were to plug in negative infinity in here and in here, 2 to the negative infinity is the same as 1 over 2 to the infinity. So therefore, what is that essentially? As infinity or this exponent gets larger, that's just going to turn into 0. So both of these will turn into 0 as x goes to negative infinity. So it looks like we get a horizontal asymptote of y equals 5. So on the left side, as x goes to negative infinity, this is our horizontal asymptote. On the right side, it looks like we're going to get something a little bit different. As we go to infinity on the right, these two values are really going to do nothing for us, right? They're finite values that in the end won't do a whole lot for us. As we go to infinity, basically what we're doing is taking the limit as x goes to infinity of 2 to the x over negative 2 to the x. So it looks like these two functions will act the same. They have the same power or strength in how they grow. So therefore we could say that this will approach negative 1. So our horizontal on the asymptote on the right side would be y equals 1. Okay, so basically throughout this lesson we're looking for where the most powerful function happens, numerator or denominator, so we could determine whether or not we have a horizontal asymptote. More powerful in the numerator, no horizontal asymptote. Two functions of equal strength on top and bottom would be their coefficients, ratio of their coefficients, and if the denominator is going to overpower the numerator, then the horizontal asymptote would be located at y equals 0.